So, lesson 7. I called this orbital mechanics. Really different questions involving energy and circular motion and going in orbit and rocket science and stuff. Kind of a mishmash. Example 1 says, a mass m is moved from the surface of a planet to a distance big R from the planet's center. Which of the following is true about the work done? A, the work is given by force times distance. B, the work is given by force times big R minus little r, where I guess little r is the radius of the Earth if I look at my picture. C, the work is given by big G, big M, little m over r squared times r minus r. D, the work is given by, which of these is right? Well, I can tell you some of these are wrong. I can't use force times distance. Why not? For force times distance to work, and we kind of forgot about this because in Physics 11 we always gave you it this way. What did we have to say about the force? Does anybody remember? What could the force not be? Changing. So force times distance only works if your force is constant. Oh, as you get further from Earth, is the gravitational force constant always the same? No. So we can't use that one. In fact, this is why we fell back on our really universal definition of work, the work energy theorem, where we said work was equal to change in potential plus change in kinetic. Now look at the picture. I think we're lifting the rocket up. It does not look like we're putting it in orbit. How do you know, Mr. Duick? I think if it was in orbit, the rocket would be tilted 90 degrees to the Earth and it would look like it was going around. Let's assume that. So I don't think there's going to be any kind of a change in kinetic for this question. So we're left with change in potential. And once again, hey, what is change in anything? So this is going to be potential energy final minus potential energy initial. Jake, can I use MGH? No. So this is where we used the new equation that we learned last day. Negative big G, big M, little m, all over. And I guess looking at my diagram, R final is capital R? Yes? Minus negative big G, big M, little m, all over. And I guess R initial in my diagram is little r. Remember, why negative? Because where did we define 0 to be for potential energy? Began with the letter I. Yeah, infinity. The phrase we used was relative to 0 at infinity. So anything less than that has to be negative. Oh, but the nice thing was it still worked. We still got positive answers when we wanted positive answers. When we were asking how much work it took, we did get a positive answer saying we had to do some work. So the minus minus took care of that and all that. Hey, which of these, you know what? I think it's this one here, isn't it? Yes? There's a minus minus in the middle, which becomes a plus. And where it says explain your answer, we just have. I have seen it because there is a G in both terms, and because there is a big M in both terms, and because there is a little m in both terms, I have occasionally seen it written factored. I have occasionally seen it written like this. They factored out the big G, the big M, the little m, and that's left them with a negative 1 over R plus 1 over little r. I'm really not a huge fan of that one because it doesn't, if you have a calculator that lets you backspace and just change the r's, in terms of typing, it doesn't save you much time. And you guys suck at fractions. Having a fraction, anyways, for what it's worth, those are equivalent. You may see that written that way once in a while, right? I pulled out GCFs. In fact, probably they would write it 1 over little r take away 1 over big R instead of going a negative plus a positive, because that's kind of sloppy math. They'd write the positive, take away the negative. Anyways, that's how much work it takes to lift something. Again, if you let it go, it'll drop. Lift something, you can imagine little invisible angels doing the work, or a rocket engine doing the work, but not putting it in orbit, just firing it straight up. What if you actually wanted to escape from the Earth's gravity? To escape from a planet's gravity means, in theory, to travel an infinite distance from the planet, to get out to relative to 0 at infinity. Practically, it means to travel far enough away from the planet that the pull of gravity has become really, really, really small, close enough to 0 that whatever. To barely escape means to escape from a planet with no kinetic energy left at the end, so you end up at rest out at infinity. To barely escape would be to fire your rocket here on the Earth, and we're going to ignore air resistance just to make the math easy. To fire your rocket here on the Earth, boom, maximum speed and shut it off, and then coast to the edge of the universe. We call that escape velocity. And if you go back to last day's lesson, where we left off, it's actually surprisingly easy to calculate. And nerdily cool. Okay. Escape velocity asks how much work is necessary to bring potential energy to 0. Now, you can solve this in terms of work. I find this easier to solve in terms of conservation of energy. I think, hey, there's a change in height and a change in speed, and I'm trying to find my initial speed. I think I would write what we're asking is how fast do you need to go on the Earth so that you can shut your engines off and coast to the edge of the universe. When you get to the edge of the universe, we want to exactly come to a stop. So what do we want our final kinetic energy to be in our magic idealized situation? Oh, and out at the edge of the universe, relative to infinity, how much potential energy do you have out there? How have we defined it? In fact, what we have is this. A half mv initial squared plus, can I use mgh or are we going cosmic here? Negative big G, big M, little m over R equals 0. You know what? I think I would just plus that negative over to the other side and get a much tidier equation, yes? Oh, and you know what? It's R initial because it was potential energy initial. Yes? Ooh! Little unusual here. What do you see? Yeah, we're not canceling. We're not asking how much work. More mass would mean you'd need more fuel to do it. But in terms of when you hit that speed, whatever that magic speed is, doesn't matter how heavy, whether it's a space shuttle or a tiny satellite, their escape velocity will be the same. Getting it to the escape velocity will require more fuel if it's the space shuttle versus a little satellite, but the escape velocity, once you get there, will be the same. And in fact, the escape velocity is that bad boy right there. How would I get it by itself? I think times by 2 and square root. I think escape velocity is going to be 2 big G, big M, all over. And if we're talking about the Earth, it'd be the radius of the Earth. If we're talking about the escape velocity of the Moon, it'd be the radius of the Moon and the mass of the Moon. If we're talking about the escape velocity of whatever. Oh, and square rooted, I said, yes? There you go. That's escape velocity to leave a planet. Now, on the Earth, we would have air resistance if we actually started from the Earth's surface. But you know what? Once we're out of the atmosphere, which is only about 150 kilometers, which doesn't add much to the actual radius of the Earth, this would be the escape velocity if once you're in orbit and you want to leave the Earth and head out to the edge of the universe, this is how fast you need to get going, point your ship away from the Earth, and then you can shut it off and coast. Which begs the question. Let's find the escape velocity for the Earth and for the Moon. Earth, Moon. Now, this formula is not on your formula sheet. And I'll be completely honest, I don't think I'm even going to ask you this on a test. I'm doing this because it's nerdily cool. It used to be part of the provincial exam curriculum, but I hadn't seen it for about 10 years, so I still covered it because officially when I read the exam specifications back when there was a provincial, there was a phrase that could be interpreted, and I didn't know anything else, escape velocity. Now, it's escape velocity. Why do you need an explanation? This is kind of cool. So we just finished saying your escape velocity is the square root of big G, 2 big G, big M over our initial. This is going to be for the Moon, big G. This is going to be mass of the Moon over radius of the Moon. And this is going to be mass of the Earth, radius of the Earth. Which one would have a smaller escape velocity, do you think? Yeah, Moon. Why? Well, less gravitational force, so it should have a smaller escape velocity. Two, 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. I've got these ones memorized again. 6.38 times 10 to the 6th. I think escape velocity, it's around 11,000. I'm going from memory, but crunch the numbers, what do you get? I think it's right around 11,000 meters per second. Or am I wrong? Oh, it is? Sorry, 11,000. So 1.1, 11,200? Is that to 3 sig figs? Yeah? Which we can do. In the atmosphere, we can even do it, although the friction causes things to heat up pretty heavily. So we prefer to get you out into the thinner atmosphere or out of the atmosphere completely and then really fire the rockets. But yeah, we can do that easily within our technology. Now, of course, this is just barely escaping Earth and then coasting. It would take you, millions of years to reach the edge of the universe. So in real life, for space travel, you'd want to continuously be accelerating somehow if you could. Escape velocity for the Moon, these numbers I don't know. Well, I know G, 6.67. Somebody, what's the mass of the Moon? It's 7.35 times 10 to the, I didn't hear the last part, 20 what? 22. And radius of the Moon, is it 86,000? No, that's wrong. 1.74 times 10 to the 6. What do you get? Do you get 2,374? Yeah? Considerably smaller. Hence, hey, if we really want to do space travel right, a moon base is almost a necessity. Well, no, maybe not. If we can find some type of source of fuel or something that we can turn into fuel on the moon, then a moon base really makes good sense. 237 meters per second. So escape velocity. Let's reverse the procedure. Instead of asking how fast to leave the Earth to go away, what if you come crashing into the Earth? How fast will you hit the Earth? This says a 3,400 kilogram mass is released from a height of 6,300 meters above the Earth. I think this is a typo, so we're going to add 63,000 meters above the Earth. "63 kilometers above the Earth." How fast will it be going when it hits the ground? Is this question asking for work? No. Is there a change in height? Is there a change in speed? This is a job for conservation of energy. Not plus heat because it says ignore air resistance. Am I going to be able to use MGH here? I think I'm going to have to use the cosmic potential energy. Let's assume, oh, it says it's released from a height, so I think we can assume we're starting from rest. This is going to be negative big G m little m over R initial equals a half little m V final squared plus negative big G big M little m all over R final. Okay, I guess they didn't need to tell me that the mass was 3,400 kilograms. I think to get rid of the one, I'm trying to find V. To get rid of the 1/2, I think I'm going to go times by 2, times by 2, times by 2, and here that'll get rid of the 1/2. Is that okay? And I also think I'm going to plus that negative over to the other side, the negative big G big, well, the negative 2 big G big. I think I'm going to get this. V final squared equals negative 2 big G big M little m all over R initial. Oh, I canceled out the little m. Thank you, Ty. Negative 2 big G big M over R final. Yeah, good gosh, Duick. Right, so we plus that guy over to that side. Except I then moved it to the right because I'd like to have my variable on the left. Getting rid of square. I think it's going to, the final thing is going to be square rooting this whole sucker. I don't think I'm going to type that all in one fell swoop. I think I'm going to type in the first expression to maybe 6 sig figs, get an answer. Second, backspace, and just change a few numbers to get the second expression to 6 figs. Add those together, press equals, and then square root. You could do this all in one step. It's going to be ugly, so I'm going to separate it. I'm going to see if I can fit this on this line. Let's find out. Negative 2, 6.67 times 10 to the negative 11. Mass of the Earth. What's my initial radius? the radius of the Earth plus, it did give me a height above the Earth of 63,000 meters, yes? Was it 63,000 meters, Mr. Dude? And then it's going to be plus the same thing, the same thing, the same thing, the same thing. I'm running out of room. Over 6.38 times 10 to the 6th. The final radius is hitting the Earth's surface. Yeah, I think. By the way, what are we talking about here? Meteorites, right? Asteroids hitting the... Well, this would be a fairly big meteorite. 3,400 kilograms. It'd probably do some damage if it made it through the Earth's atmosphere. Thankfully, most of them burn up. So, -2 times 6.67, -11 times 5.98, 24 divided by bracket 6.38 times 10 to the 6 plus 63,000. So the first one I get -1238. Okay, 1, 2, 3, 4, 5, 6, 7, 8. -1.238 times 10 to the 8th. The second one, I lose the negative, boom, and I lose the 63,000, but everything else is the same, right? I get 1, 2, 3, 4, 5, 6, 7, 8, 1.25, let me say figs 4, 1.250 times 10 to the 8th. So I take that and I subtract the first number, 1.238 times 10 to the 8th. And then I square root. And it's coming in at about just over 1 kilometer a second. Is that fast? It'll get your attention. In fact, if there was no air resistance, if we had no atmosphere, say, like the moon, I could figure out the kinetic energy, which would be this squared times a half times m. What did I say the mass was? 3,600? 3,400? That's going to leave a fair-sized crater. Hence the moon's landscape. Oh, yeah, and we get hit by big ones every few million years, and we're due, right? So, I think I'm still okay with that homework from last day. Let's go back to our current lesson that we are on now. Here. This, Josh, is why I was ranting as I came in this morning, because I looked at this and I went, oh, here I'm talking about escape velocity again, which I sort of meant to cover last. I need to kind of smoosh these lessons a bit better, because it says, to escape from a planet's gravity means, in theory, to travel an infinite distance from the planet. Practically, it means to travel far enough away from the planet. So that, I think I just read this already. So that the pull of gravity has become very small. To barely escape means to escape from a planet with no kinetic energy left at the end. So you end up at rest at an infinite distance. The shortcut to escape velocity is to realize all of your initial kinetic has to become all of your initial potential. Except negative, because you want negatives to cancel. Right? This was really us saying kinetic energy initial plus potential energy initial equals 0. And then you can derive it yourself. Okay. So example 2 says a 12,500 kilogram rocket blasts off from the Earth and barely escapes the Earth's gravity with no additional engine use. How fast was the rocket moving at launch? I'm hungry. At launch? Well, wasn't it 11,100? That was the escape velocity of the Earth, I seem to recall. John, is that what you said it was? Yeah. Oh, did the math? 11,200? Oh, ooh. I guess that means you wouldn't quite get there, so that's important. If I was a little over, that'd be okay. I'd have some energy left over at the edge of the universe. Did we say the masses cancel? Oh, then we're done. We could recrunch it, but we did it 5 minutes ago. Right? Now we can turn the page. Here is a more rocket science-ish question. So we have a stationary, initial kinetic energy is 0, 12,500 kilogram rocket. It blasts off from the Earth and it enters into a circular orbit 25,500 kilometers from the center of the planet. Okay, so that's a radius they gave me, because they said from the center of the planet, so I'm not going to need to add the Earth's radius. It's in kilometers. I'll have to do the unit conversion. I'll just times by 1,000, easy enough to do. A says, write a work energy equation. Okay. Done. B says, find a bunch of stuff. Okay. First thing it wants me to find is its orbital speed. How do we find orbital speed? What is it, Dorothy? Although I usually wrote Fg equals Fc. But yeah, it's, you know what? Gravity is pulling me in a circle. The only reason I put the Fc on that side is I'm trying to reinforce Fc is your net force. When you move it, it's your winner minus loser equals that thing, right? Gravity is always big G, big M, little m over r squared. Fc is little m times which one? Oh, orbital speed. I want the v squared over r, yes? And we've seen this a few times where, hey, and yay. In fact, you may have this one memorized already. I guess if you do, I won't freak out if you don't walk through the steps. I just consider it a waste of memory because it's 2 lines to get there. Turns out orbital velocity is big G, big M over r, square rooted. Which is going to be, because I'm running out of room, I'm just going to write big G. I know it's 6.67 times 10 to the negative 11, but I notice I'm finding 5 things, and I have one. I'm going to have to write small here. So mass of the Earth, 5.98 times 10 to the 24th, all over. R is orbital radius. What did we say it was? 25,500 kilometers, which is going to be 255,000. 2.55 times 10 to the 1, 2, 3, 4, 5, 6, 7. I'm going to write that right here. R equals 2.55 times 10 to the 7th, because that's easier to type than 25,500. Anyways, 2.55. What's its orbital speed? You get 3,955? So I'm going to call that 3.95 times 10 to the... Well, you know what I'm going to do? I'm going to go 3,955. Is that okay, Dorothy? Yeah? Okay. And then I'll go sig figs. 3.95 times 10 to the 10 to the 10 to the... Mr. Duick, why didn't you round off to 3.96? Because it's actually not... It's a 4 after there. I'm not going to round off and round... Anyways, meters per second. 10 to the what? Third. Meters per second. I kept the extra digits because I glanced at part 2, because what does part 2 want me to find? What's the second thing they want? Next thing they want me to find? Kinetic energy. You know what? That's a half mv squared. I may as well keep a few extra digits of my v, right? This does depend on the mass. Bigger mass needs more energy. Hence, we try and build stuff lightweight. Sorry? I don't know. Read the question out loud to me. What's the second word? Ah, there you go. Now, this is where, remember last day I said we're going to fib. We're going to assume it has no kinetic energy. Technically, they all do because they have the kinetic energy of the Earth's rotation. But how much depends on your latitude. Blah, blah, blah. Magic physics world, make the math easy. Conveniently, I have this number here, squared times 0.5 times 12,500. And I get a kinetic energy of 9.776, 9.78 times 10 to the 10th, holy smokes. And energy is joules. All right. What's the third thing they want me to find? Potential energy in orbit. Okay. Negative big G, big M, little m over r. And I guess potential energy in orbit is going to be radius in orbit. Is going to be negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th, 12,500 divided by 2.55 times 10 to the 7th squared. No, energy is not squared. Negative 6.67 negative 11 times 5.98 times 12,500 divided by 2.55 7. And I get negative 1.955, negative 1.96 times 10 to the 11th. Yeah? By the way, these are all the different things I can ask you in this kind of a situation on a written question. I'd probably ask you only 2, not 5 things, but one would be worth 4 marks, one would be worth 3 marks, it was out of 7, something like that. Jason, what's the next thing you want me to find? Oh, total energy. How do you think I'd find the total energy? What does the word total mean? Add them up. Not changing, total, right? Add them up. Total energy, how about TE for total energy? Brand new abbreviation, but works for me. Equals KE plus PE in orbit and in orbit. 9.78 times 10 to the 10th plus negative 1.96 times 10 to the 11th. Now we are going to get a negative answer because relative to 0 at infinity, the amount of energy it has in orbit is negative. Why? Because you would have to add energy to get out to infinity. And if you want to add something but end up at 0, you better start out with a negative number, right? Conveniently, I have that, so it's going to be that number there plus 9.78 to the 10th. Negative 9.77 times 10 to the 10th. I'm going to do that with a little more accuracy. I seem to recall that this was actually 9.776 times 10 to the 10th. Yeah, you know what? It's not negative 9.77. If I go a little more accurate, it's actually negative 9.78. Why is that kind of an interesting answer? What? This looks like it's the same magnitude as the, looks like the total energy is the same magnitude as the kinetic, but negative. I wonder if that's always true. Yes, we'll prove it in a bit. Oh, and it looks like if you divide this number by 2, you'll get this number. Or this number, but negative. Anyways, that's total energy. Fourth thing they want us to find, PE at launch. Or fifth thing, I think that would be PE initial, which is going to be negative big G, big M, little m, all over R initial is going to be negative 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 12,500. None of that changes. Our initial radius, oh, we started out on the Earth's surface, so 6.38 times 10 to the 6. Okay, I got most of this already. Negative 6 point blah, 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 blah. Just change this number, Mr. Duick. 6.38 times 10 to the 6th, I think. I'm starting out with negative 7.81477, negative 7.81 times 10 to the 11th. What's the last thing they want? Work required. Okay. Here we go. This is where we're going to say work is change in kinetic and change in potential. Or change in potential and change in kinetic. Dorothy, how much kinetic did we have at the beginning? What did we end up with in orbit? We did crunch that somewhere. That was 9.78, was it? Okay. So we have that much to keep it in orbit. Change in anything is final minus initial. Our final potential energy in orbit was negative 1.96 times 10 to the 11th minus. Our initial potential energy was negative 7.81 times 10 to the 11th. .78, 10 to the 10th, plus, I'll do this in brackets, negative 1.96, 11. What's a minus minus the same as? I'm just going to go plus 7.81 to the 11th. How much work? That much work. 6.83. Times 10 to the 11th joules. What does the work? The rocket engine's the fuel. And again, you're seeing big exponents, 10 to the 10th, 10 to the 11th. That's why it's so expensive to put stuff up there. Is that okay? A little bit more and we're done. Example 4 says, using the expression for orbit speed, which is that, prove that in a circular orbit, the kinetic energy is half the magnitude of the potential energy. Okay, well, first of all, potential energy is negative big G, big M, little m over R in orbit. Kinetic energy is a half mv squared. And I kind of walked through this a tiny bit with you last day. If we replace the v squared with that thing, oh, and this is kind of nice because if I square the v, just the square root vanishes. Yes? We get a half little m big G big M over R orbit. And if I take that little m that's in the front and I tack it onto the end where we're used to seeing it, we get big G, big M, little m over R orbit with a half in front, which I'm pretty sure is half of the magnitude of the potential energy. It's positive where the other one is negative, but that's why I said half of the magnitude. Do you need to know that, Chelsea? No, but it's nerdily cool. I do kind of use that as an error check. In other words, if I'm doing the previous question, for example, you'll notice when I got the 9.77, I went, you know what, I know it's supposed to be 9.78. I'll fix that, and that way I've taken care of any rounding error. That's all I use it for. It also says prove that the total energy is half the potential energy. Well, total energy in orbit is potential energy in orbit plus kinetic energy in orbit. Check. Which is going to be negative big G, big M, little m all over R. Plus, now I was going to write a half mv squared, but you know what I'm going to write instead? My expression right above there. A half big G, big M, little m over R. Now, those are fairly ugly expressions, but look, are those not like terms? Is there not a big G in everything, a big M in everything, a little m in everything, and an R in everything? Isn't this really negative 1x plus a half x, except instead of an x, it's a... Oh, what is negative 1 plus a half? Really? I get to my big punchline, and that's where you die? You follow the variables, and when I say, what's negative 1 plus a half, your brains cramp up. As I've said, your generation sucks at fractions. Please help me, John. What is it? Ah, so you're saying that this is really negative a half. Let's write that a little neater, Mr. Dewick. Big G, big M, little m over R, which is half the potential energy. You want to know the total energy you have in orbit? It's half the potential. That's not how much work, by the way, though, because that assumes that if that was how much work, that would assume you started from the center of the Earth, which we don't. We have a head start. We're on the Earth's surface. So the amount of work to get there is always a little less than that. Oh, and then 3 says, prove the total orbit energy, E, is the opposite of the kinetic energy. Are those exactly the same but opposite? It is. Duh. Okay. I'm not quite sure. What do you want for a proof? It is. I can. Hello. They're this.
Do we need to know like the proofs and stuff at the time?
No, I show them to you because I think it helps you understand where they come from better. Sorry, that's a lie. You are going to need to know the Fg equals Fc, how to derive any of those other ones. And those are technically proofs, by the way. What you're doing is you're proving what orbital speed is, or what orbital period is, or what orbital radius is. And those are the three I'm going to test you on. You're either going to find an orbital speed. If I do that, I'll give you the radius. Or you're going to find the orbital period. If I do that, I'll give you the radius. Or if I give you the period or the speed, I'll ask you to find the orbital radius, going backwards. Or I can give you the period and say find the speed. Usually if they give me the period, I'll find the radius and then use the radius to find the speed. But anyways, any one lets me find any of the other two. Starting out each time with Fg equals Fc, and then away I go. Now, work, different approach, and no pun intended, a lot more work. I'm not wild about, this is this other section I was ranting and raving about. I think I'm going to pass on that, and I'm going to say try number 1. Number 3, that's a lengthy, challenging, lots of work question. There they're giving you the radius. Once you have, oh, by the way, they're giving you the radius in kilometers, but it is a radius because it does say from the moon center. You'll have to find its orbital speed. And then, anyways. 4 is good. 5 is good. 7 is good. Now, number 7 says, a rocket blasts off from the Earth moving that fast. The rocket has a mass of that much. Find the maximum distance from the center of the Earth the rocket reaches before stopping. This is not a work question, but there is a change in height. There is a change in energy. This is a conservation of energy question. Oh, and if you're getting the maximum distance, really this is like throwing a rock in the air, but we're doing it on the cosmic scale. When you throw a rock in the air, what's your final kinetic energy at the top for a split second? 0. When you launch a rocket and see how high it gets from a planet before it comes crashing back down, what's your final kinetic energy for a split second? 0. So the only difference is you're not using MGH, you're using the Yakir cosmic potential energy equation. That's a nice one. 8 as well. 9, 10, 11 we've already done in our notes. Don't need that. I think we're good there. Oh.